All right, so today we'll finish up section 5.1. Okay, we already talked about how we graph polar coordinate. Talked about different ways to represent it, whether you're going clockwise, counterclockwise. We changed polar to rectangular. And then today we're going to do the other thing. We're going to change it from rectangular to polar. All right, so if you start out with a point in rectangular, what does that look like? What are the two things that they give you if it's a rectangular point? They give you an x and a y. And our goal to get it in polar isn't to have an x and a y. What do you want to have in polar? You want r and theta. Good. Okay, so they'd be starting me off with an x and a y. Okay, so here's a point. It's got coordinates x, y. What shape do you think I could draw here that would help me, kind of like we did last time? Yep, we're going to make a triangle. So I'm going to draw in that. And draw a line straight down from the point to the x-axis. There's my 90-degree angle. Okay, the length of the bottom side of the triangle, that's x. It's the horizontal distance you need to go over to get to the point. And then the height you got to go, that's y, to reach that point. What would the hypotenuse be here in terms of a polar coordinate? It's a hypotenuse, but it's also what other value? Yeah, that's the radius, the distance from the center to the edge. Okay, so we need to find the radius. And then the angle, well, we just formed that by making a triangle. That's my angle. Okay, let's start with finding r. If you knew x and you knew y, you know 2 out of 3 sides, how can you find the third side in a triangle? Yeah, the Pythagorean theorem. Okay, so you're going to just do x squared plus y squared equals r squared. Okay, and I'll write this on the next page as a series of steps. I'm just showing you where the steps are going to come from. And then the last thing is take the square root of each side. Because I don't want to have r squared, I want r. When you take the square root of a sum, can I cancel the square roots on those x's and y's? Or cancel out those exponents? Well, let's try it. If we took 4 squared plus 3 squared. Let's say we do the order of operations. 4 squared is 16, 3 squared is 9, 16 plus 9 is 25, and the square root gives me 5. Okay, if we cancel the squares, and you say, oh, that's going to cancel, you'd get 4 plus 3. Did it come out the same? No. So you can't cancel those exponents. There's an example that shows you it doesn't work. Okay, so you got to do that out. So there's your radius. Okay, next thing we need to figure out is the angle. So what are the names of the 2 sides that I know relative to their position to that angle? They're the x and the y, but what's the y? That's opposite. Yep. And what about the x? That's adjacent. Which trig function has those 2 in it? Bless you. Which trig function has opposite and adjacent? Tangent. Okay, so we're going to set up our formula to find theta. Tangent theta equals opposite over adjacent. Okay, now the problem is I want theta alone. I don't want the tangent of theta, I want theta. So how are we going to get rid of tangent? Yep, we're going to take inverse tangent. On the left. On the right. Bless you. And theta is the inverse tangent of y over x. Okay, so that's where our formulas are going to come from. Now I'll kind of write out the steps for you a little bit more formally. Okay, so to convert from rectangular to polar, first thing you want to do is take your point, graph it, and figure out which quadrant it's in. Okay, the reason you have to figure out which quadrant it's in has to do with theta. It doesn't have anything to do with r. Quadrant doesn't matter for r, but it does matter for theta, and I'll show you why. So if theta is in quadrants 1 or 4, and again, you're going to know the quadrant because you're going to graph it. You're going to have a point like 2, 7. Graph it, see the quadrant it's in. The formula for theta is the formula we just came up with. Inverse tangent of y over x. Okay, the problem with doing inverse tangent, though, is you're always going to get an answer between negative 90 and 90. Negative 90 is down here. Positive 90 is up here. So you're always going to be getting an answer somewhere in one of these two quadrants. Okay? That's quadrant 1 and quadrant 4. If you just use inverse tangent of y over x, you would never get an answer in quadrant 2 or 3. But it's easily possible to have a point there. So if we're in quadrant 2 or 3, we pretty much use the same formula. It says inverse tangent of y over x, but we have to add 180. Or if you're working in radians, you have to add pi. Okay, so only for quadrants 2 and 3, you got to do your inverse tangent of y over x, just like we did before, but then take and add 180 to your answer, if you're doing degrees, or pi, if you're doing radians. That's why the quadrant is important. Okay, if you're on an axis, what could happen there? Think about if you were at the point, let's say you just went up 1. What's the coordinate if you go up 1?
0, 1.
0, 1. And that's on an axis. X is 0, y is 1. What happens if you try to plug in a 1 in the top here and a 0 in the bottom? Yeah, you can't divide by 0. Okay? So these formulas only work where I'm labeling they work. Quadrant 1 or 4, quadrant 2 or 3. If you're in between quadrants, or you're on an axis, you pretty much just have to look at that and identify the angle yourself. If you're straight up, that's 90. If you're to the left, what angle is if you go left 1? That's 180. It's 90. How about if you went straight down? What angle is that? Yep, negative 90, which is the same as positive 270. And then we started out at 0, which is the same as 360. Okay? So if you're on an axis, your angle is either 0, 90, 180, or 270. You don't use one of these formulas. They won't work out right. So that's the easiest case.
So if it's like that, you just, like, wherever the point is, and then the angle to make it polar.
If it's on an axis?
Yeah.
Yeah, if it's on an axis, you'll see it's going to turn out really easy. Yeah. Okay. The reason it's going to turn out so easy is on an axis, one of your x's and y's, one of them is 0. So whatever one is 0, when you use the Pythagorean theorem, that one just disappears, because anything squared stays 0. You can still use the Pythagorean theorem, it becomes very simple. Okay, and then to determine your radius, this Pythagorean theorem works in any quadrant. It doesn't matter, 1, 2, 3, or 4. Or on an axis, it works there as well. Any questions on your formulas for finding theta or finding r? Now the way I did it, I said to find theta first and then determine r. It doesn't really matter. If you want to find r first and then find theta, that's fine. They're separate. All right, so let's try this one. Convert 2, -2 to polar. Before I really start doing any arithmetic, what do I have to determine first? I got to determine what quadrant it's in. Okay, so we're going right 2, down 2. Doesn't have to be an exact sketch. I just need the quadrant. It's quadrant 4. Okay, so let's start with theta. In quadrant 4, do I need to add 180 to my answer? Nope. It's just the inverse tangent of what goes on top, x or y? Y. Inverse tangent of y over x. Okay, so just type that in. And we'll get our angle. Unless they specify what units, you can use any units you want. I'm going to do it in degrees. So when I hit enter, the calculator will give me an answer in degrees. So inverse tangent of -2 divided by 2. Okay, -45. Something I might do on the test is say, express all your angles as positive. Well, how would you make -45 positive? Just add 360, and you get 315. Oh, I didn't get plus. So there's 315. If the directions don't say, you can leave your angle negative. That's fine. But generally, I like to think it as a positive angle, then I only have to think about going in one direction all the time, not thinking about which way am I moving. Okay, so there's my angle. Okay, and lastly, let's find the radius. So r equals the square root of 2 squared plus -2 squared. Okay, Naisha, what's 2 squared? Whoops. 4? How about -2 squared? So -2 squared, that's -2 times -2. Still 4. So I get the square root of 8. And how does the square root of 8 reduce? So we talked about that very first day when we did distance formula. Yep, and how'd you do that? You do 4 times 2. Yep.
And then you factor 2 from the 4. Like, I don't know how to describe it. You can take the 2 out of 4.
So you factored the 8 as 4, yeah, 4 times square root of 4 times square root of 2.
Yeah.
And now just do it out. That's all. Just take the square root of 4. 2.
Oh, okay. I don't know how to describe it.
Yep. But that's good. That is the right answer. So 2 square roots of 2. Okay, so the exact answer to this problem is 2 root 2, comma 315. If they wanted a decimal for that, you could just use your calculator and find the square root of 8. It's about 2.83. I would make sure you know how to reduce the square root for the test. It's probably going to come up. All right. This is the exact, and this one is approximate. Okay, any question on that? So that's how you convert a point from rectangular to polar. if it's in quadrants 1 or 4. Yeah, let's try one in quadrants either 2 or 3. Which quadrant is that point going to be in? -4, -5? Yep, that's in 3. Left 4, down 5, somewhere in quadrant 3. So to find my angle in quadrant 3, what do I have to do extra this time? If I'm doing it in degrees, I got to add 180. Plus the inverse tangent. Now you got to be careful, since last time I had a 2 and a -2. If you switch them, it wouldn't mess it up. But this time the numbers are different. Okay, so what goes on top here? -5, yep. And if you want, you can cancel the negatives when you type it in. So it's the 180 plus the inverse tangent of 5/4. Okay, so we don't get a very nice answer here, and that's fine. So it's 231.34. Okay, so there's theta. And Zach, how do I find my radius?
You would do the negative tangent of -4 over -5.
So anytime you use a inverse trig function, that's to find an angle. So we've already used the inverse trig function. We already have the angle. So anybody remember how we find that radius? It's really what theorem? Yeah. Yeah. Yeah, it's the Pythagorean theorem. If you think of this as a triangle, let's see, this side's 4, this side's 5, just find the hypotenuse. Okay? Whether or not you use the negative, it doesn't matter. It's going to cancel out. So it's -4 squared plus -5 squared, and you need the square root of that. Okay, so I square -4, and that's going to give me, how much, Ashley? 16. And Olivia, -5 squared? 25. Add them up. 16 and 25 gives me square root of 41. And that's not going to come out nice. Okay, if there was if it's divisible by a perfect square, that's when you can reduce it. This one is not. So either leave it as the square root of 41 if they want it exact. Since we already rounded our angle, I'm just going to round the radius as well. 6.40. Okay, and that's pretty much it. So now just write your coordinate. R theta. Okay, any questions on converting from rectangular to polar? That's all there is to it.
What's the
R, to find R, you're using the Pythagorean theorem. Pretty much, yep. R squared equals x squared plus y squared. Okay, anything else on section 5.1? So next we're going to take a look at section A.4. Okay, A.4 gets into complex numbers. Okay, you've probably already done complex numbers in Algebra 2. So we'll do a quick review here. First thing I'm going to do is I'm just going to write down kind of the different numbers that we know, different types of numbers, and then where do complex numbers and imaginary numbers fit in. Okay, because using those words interchangeably, they're not the same thing. Right? They're different categories. So the most basic kind of numbers that you can have are your whole numbers. Actually, even basic counting numbers. Counting numbers are even more basic. They don't include fractions and decimals. They don't include negatives. They don't include 0. Okay, think of how you count things. 1, 2, 3, 4, 5. They start at 1, no fractions or decimals, and they go up from there. Okay, the problem, if you only allow yourself to use counting numbers, okay, remember, counting numbers don't include 0. 3 is a counting number. 3 is a counting number again. What would happen if you do 3 minus 3? What do you get?
0.
0. But is 0 a counting number? No. So unless you're going to invent a new kind of number that means having nothing, you can't do 3 take away 3. Not with just counting numbers. You need another type of number, and those are your whole numbers. Okay, whole numbers allow you to do more kinds of calculations that you can't do if you don't have the number 0. So now I can do 3 take away 3, and I could answer that question. But how about if I took 6, which is a whole number, 8, which is a whole number, and subtracted them? Is the answer a whole number? No. So if you show that to somebody that's in first or second grade and they don't know about negatives yet, they'd say, well, you can't do that. They'd write undefined. Or they'd say they don't know. Because you can't take away more than you have unless you're going to invent a new kind of number that means taking away more than you have. And those are your negatives. And the set of numbers that now includes your negatives, those are your integers. Okay, so with each number set, all we're allowing ourselves to do is more kinds of calculations. So far, these calculations could come up in everyday life pretty easily. If you have $10 in your wallet and you spend all 10, you have nothing left. Okay? As we start to get to more and more complicated number sets, that's when we start to get more theoretical. Okay? Less application to real life, but we're still very much in real life. Okay? People go in debt all the time. They spend more money than they have, so negative numbers still pretty important. With integers, you can pretty much do addition, subtraction, and multiplication with no problem. If you multiply 2 integers, if you add 2 integers, or subtract 2 integers, you always get an integer as an answer. How about if I divide 2 integers? Does the answer always come out to an integer? You could get a decimal. So if I took 3 and I divide by 2, 3 is an integer, 2 is an integer. If you don't understand fractions or parts of things, you can't do that. That's impossible. In real objects, that's impossible. You can't take 3 objects and divide them equally between 2 people. That can't be done. So then we have to start breaking things into pieces. Okay? And that's where we get our rational numbers. And I'd say rationals are still important for pretty much everyday life. If you're cooking, you might use 2/3 of a cup. You're not using 1 cup. You're not using 0 cups. You're using a fraction of a cup. That makes sense. When we start to get beyond rationals, now the applications to everyday kind of stuff get more limited. Okay. Anybody know what kind of the counterpart is to rationals? You have rationals and irrationals. So irrationals are all those numbers that they never end. They don't have a decimal that repeats. They can't be written as a fraction. So pi, okay, there's no pattern to pi. It never ends. It doesn't repeat. If you had something like 0.3 repeating, okay, that's different. That is rational. You can write it as 1/3. So it can't keep repeating. There's no pattern to it. Square roots. If you take the square root of any number that's not a perfect square, like the square root of 5, it's irrational. Okay, there's no pattern. It doesn't repeat. If you take the square root of a number like 9, that's different. That's a perfect square. That one works out nice. Okay, and together, when you take all your rationals and irrationals, these make up the reals. So up through algebra 1, those are the only kinds of numbers you study, for the most part. Okay, in algebra 2, we add in imaginary numbers. So imaginary numbers come up when you try to take, for example, the square root of a negative. Okay, try it on this calculator. It says invalid. Okay, this calculator basically only understands numbers up through algebra 1. It's saying undefined. Just like if you ask someone to do 3 divided by 2, if they don't understand fractions, it'd say you can't do that. It's not practically possible. Okay? But we can do that, square root, if we allow ourselves to extend our number system one more time, just like we've been doing all along. Again, I'm not going to get into the applications, because the applications of imaginary are far beyond what we're going to do in this class. Okay, we're not going to do applications of imaginaries at all. Okay, but instead of letting my calculator use reals, I can change the mode on it so it uses imaginaries. And now it'll give me an answer to that question. It says 2i. If I put it back in real and hit enter, it would say error. So you can't do it. Okay, and together you take all your reals and imaginaries, those make up your complex numbers. So complex numbers have a real part and an imaginary part. Every single number you've ever learned about, okay, is a complex number. Okay? Even the number 2, okay, a simple number, 2. What we normally don't write is the imaginary part. 0 imaginary parts. If something has 0, we normally don't write it. Okay? So you just see it like this. Okay? But 2 is still a complex number. It just doesn't have an imaginary part. Okay? So that's kind of where imaginaries, complex numbers, and everything kind of fits into the big picture. So now let's talk about complex numbers. Okay, a complex number is written in the form a plus bi. And that's called the standard form of a complex number. The real part always comes first. And then the imaginary part is just the b. The I next to it tells you that b is imaginary. So there's an example of a complex number. 2 plus 3i. What's the real part in 2 plus 3i? 2? Yep. And what's the imaginary part? Just 3. So the real part's 2, and the imaginary part is 3. Okay. Sometimes you might have a complex number written, and it doesn't have a real part. Okay. I gave you an example earlier of something that didn't have an imaginary part, 0i. Well, if we have something that doesn't have a real part, the only thing it has is an imaginary part, that's called a pure imaginary number. Okay? Like 4i. There is no real part. You could think of it as this. 0 plus 4i. But again, if something's 0, we normally don't write it. Any questions on how you write a complex number, what the standard form of it is, or what a pure imaginary number is? All right, quality of complex numbers. So what does it mean for two complex numbers to be equal? Well, if we compare two real numbers, okay, that's a little easier because real numbers don't have two parts to them. Complex numbers do. So if we had two complex numbers, I'm just using letters, a plus bi is one of them, c plus di is the other one. You have to compare two things here to see if those numbers are equal. First, you'd have to check and make sure that the real parts match. So A would have to match C. And then you have to check that the imaginary parts match. B would have to match D. Okay, it's pretty much common sense, but it's not something we have to do with real numbers. We only have to check one thing. With complex numbers, you got to check two. So for example, 3 plus 8i is the same as 3 plus 8i. How about if I did 4 plus 2i and 4 minus 2i? Are those the same? Okay, does it fit that definition?
No.
Does A match C? Yep, that does. 4 matches 4, but 2 doesn't match negative 2. So these would not be considered equal. Parts of them are, but not the whole thing. Okay, and one thing that you got to be careful of when you decide, okay, I'm going to use a new type of number system, whether you're going to allow integers or rationals or irrationals, you can't assume that everything you knew about numbers before still works. Okay, so because we're using or inventing a new kind of number system, okay, complex imaginary numbers, we can't assume that what we knew before about addition, subtraction, multiplication, and division, we can't assume that it still works. It might not. Okay, lucky for us, most things that you already know about real numbers, they do apply to complex numbers. Most things work just fine, which simplifies what we're doing. Okay, so to add two complex numbers, you kind of want to think of it as combining your like terms. What do you think your like terms would be in a complex number? Yeah, the reals and the imaginaries. Okay, you can combine real numbers with real numbers, and you can combine imaginary numbers with imaginary numbers. So, if you had to add these up, you'd add A to C. That would be the real part. And then you'd add B to D and put an I after it. That'd be the imaginary part. Now, we haven't even really defined what I is yet. Okay, I, when you're talking about complex numbers, is not a letter. It represents a number. Okay, and the number that it represents is this, the square root of -1. If you type that in on your calculator, that's exactly what you'll get. The square root of -1 is I. So even though I is a number, for the purpose of adding, if you think of it as a letter, it makes it easier to do. If you think of like 2x plus 3x, that gives you 5x. Well, if you think of 2i plus 3i, do it exactly the same way you do the problem up above. 5i. So even though it's not a letter, treating it that way makes it more familiar with something you already know. All right, let's try to add those up. So we've got 3 plus 8i plus 8 plus 2i. Okay, let's start with the real part. Okay, Owen, what's my real part there? Yep, 11. 8 plus 3 gives me 11. And Josh, what about the imaginary part?
10i.
10i. That's it. That's how you add two complex numbers. Addition and subtraction are the easiest ones. Multiplication's a little harder. Division, it's a little harder. But we'll talk about those later. All right, 4 minus 2i plus 3 minus 8i. Kyle, what's my my real part here?
7.
Yep, 7. Plus, Andrew, what's my imaginary part?
Negative 10i.
Good, negative 2 plus negative 8 is negative 10i. So you can write it as 7 plus negative 10i. Or how could I simplify that? Yeah, you could just write 7 minus 10i. That's still standard form. Whether there's a plus or a minus, it doesn't matter. Okay, let's try one more with addition. Okay, negative 3 minus 4i plus negative 7 plus 8i. Okay, Brandon, what's my real part here?
Negative 3, negative 7.
Yep, and then when you add them up,
Negative 10.
good. Negative 10. And the imaginary part, I got negative 4 plus 8i. That's 4i. Okay, any question on addition? Let's look at subtraction. Okay, subtraction is it's pretty much the same thing, except you have a subtraction sign between. And the only thing you want to be careful of is that subtraction sign is distributed to the real part and the imaginary part. Some people forget that it also goes to the imaginary. So in this case, you'd do A minus C, and then B minus D, with an I at the end. But you're still combining like terms, just like we did before. Combine real parts with real parts and imaginaries with imaginaries. Okay, so first subtraction, 2a. 4 plus 12i. Take away 3 plus 4i. Okay, Sean, when you do that out, what would be the real part of my answer?
Well, I guess maybe 1 plus 8i.
Yeah, but that's actually the whole thing. So the real part is 1, so that's good, 4 minus 3. And then the imaginary, 12, take away 4 is 8. I. Good. Yep, that's the whole thing. Okay, and let's just try one more with subtraction. 3 minus 5i minus 8 minus 6i. So Amy, what would be my real part there? Go ahead, one more time. Yep, negative 5. So she did 3 minus 8. That's negative 5. And Adam, my imaginary part?
Negative 11.
Okay, what did you do to get that?
Negative 5 minus negative 6.
Okay, so that is correct. What happens when you do negative 5 minus negative 6?
It's negative 5 plus 6.
Yeah. So what would that give me for an imaginary part?
1.
1i. Okay, or when the imaginary part is just a 1, we can write I. You don't need to write 1i. Okay, any question on that? All right, so earlier I said to you that I is the square root of negative 1. Okay, that's not something I can prove to you. That's a definition. That's a fact. Okay? We needed some way to represent the square root of a negative number. So somebody decided to say, okay, we'll just call it I. Right? That's just what it's called. And now from that fact, which we just take as a given fact, then we can do other things from it. Like this. Let's figure out I squared. What does I squared mean? If you had to write that out for somebody that didn't understand exponents.
Square root of -1 times square root of -1.
Yeah, so it means to take I and multiply it by itself. That's what squared means. Do I times I. Okay, and as Andy just said, you got the square root of -1, that's I, times the square root of -1 again. Oops. So what would that come out to? That comes out to -1. When you multiply two square roots together and the radicands are the same, the roots just cancel and the answer is whatever is underneath. Okay? You can think of it this way. It's the square root of -1 squared. The square and the square root cancel. That's another way to think of it. And you get just -1. Okay, when we start to multiply complex numbers, I squared is going to come up a lot. And it's going to be important that we never leave I squared in the final answer, that we always change it to a -1. Okay, as far as like I cubed or I to the 4th or any other power, we're not going to really deal with that at all. Just I, and now I squared. Okay, any questions why I squared is -1? Okay. So I think that'll be a good spot to pick up with tomorrow. Okay, so the first page of homework, that's on converting between the polar and rectangular. Page 308, 55 to 65 all. And page 560, it's on the complex numbers, 9 to 14 all. So tomorrow we'll finish up complex numbers and we'll start to learn the connection between polar and complex.